Well, first of all, thank you everybody for coming, because I'm also part of the organizing committee from DigiShape, so it's really nice to see so many people here interested in the same topics, because that's how you start collaboration, so it's nice. And yeah, today I'm going to talk about 3 different cases of different things that I've done with sensors for dikes with students. So I call the talk 3 studies from 3 students and a postdoc, because the postdoc worked with me 2 years. And yeah, basically he has helped me with a lot of the stuff here, but normally this type of work is also not necessarily recognized unless you're an author. But in reality, he helped me to supervise also a lot of these students, and now he's a postdoc in another group here in geoscience. So before we start, it will be nice to clarify or to help a bit the use of the term machine learning and artificial intelligence. I always take these talks to use this as an opportunity to explain these things. But basically, let's say that artificial intelligence is intelligence, so basically we want to mimic human behavior. We want to do things that humans can do. For example, inspection of dikes. Until now, I would like somebody to disagree with me, but until now there's no better inspection method than a supervisor walking on top of a dike. And the reason is because he's aware of too many things, and he is basically responding to too many things at the same time. His feeling, his smell, he's walking also on the dike, so he feels if the dike is soft or not. So there's not going to be, I don't see in the future something better than an inspector. However, the use of machine learning and artificial intelligence for this task is because basically, to my point of view, the system is too big. But therefore, what is the difference between artificial intelligence and machine learning? Well, machine learning is things that you use to learn. So for example, when I am a kid, I can learn the multiplication tables, right? But I don't know what to do with them. I can see it. I have a 5-year-old daughter, and now she's learning a bit of multiplication, but still she doesn't really understand what to do with them. And in the reasoning process and in the learning process, she will learn in the future that these tables can be used, for example, to calculate proportions or to calculate number of things that are happening. But for the time being, she's only learning that 2 times 1 is 2, okay? So this is machine learning, whereas artificial intelligence is the thought process after learning. And then you have deep learning, which is something that is very clear in literature and very clear in the use, let's say, in the daily basis. Deep learning is just a subset of machine learning. And it's basically machine learning which is fundamentally based or supported by way more complex and bigger, let's say, neural networks, if we put it like that. It's not necessarily like that, but it's a very good way to understand if we're working in deep learning or not. And these are basically the verbs that you can attribute to each of the different components. And how do sensors play a role here? Well, sensors can be used to collect data, and that data I use to train my machine learning models, which means that the sensors were used before using the machine learning, but I can also use them to monitor a system and take the signal of the sensor, propagate it to the already trained model, and do a prediction, which means that in the line of thinking, training, and in the track, let's say, of how we build and we use these models, the sensors are located in different places of the track. And that also has an implication because of their location and resolution. So if I am going to monitor a system, I first need to think what is the most smart way to install the sensors. But if I'm going to train a system based on what it is, the sensors were already there. So there's a bit less flexibility, so I need to use the data that is there to be able to train my models in the most efficient way so that I can come out with the best prediction with what the sensors are already delivering. So there are moments in which we need machine learning to extract the data from the sensors, but there's also moments in which we need the sensors to be able to make the machine learning perform correctly. And finally, we have this crazy thing which is reinforced learning, and I don't know how familiar you are with it, but basically every time that you ask a question to ChatGPT and there's a finger like this or a finger like this, basically we're giving a cookie to the algorithm in which we are saying, you did good, so continue doing this. So it's a bit of a hybrid problem because it happens during training, but meanwhile using. So it's a bit a hybrid thing, but it's a really interesting algorithm. And we are not going to talk about that today. So how this connects to the talk of today? Well, again, as I say, we have 3,500 kilometers of primary flood defenses in the Netherlands. We have 14,000 or more of regional defenses. The regional defenses are inland, let's say, in the compartmentalization of the country. And that's a bit more complicated because they were built in a more organic way, whereas the primary defenses have a more, let's say, strict standards, which means that there's a lot of heterogeneity among them, okay? And then basically we have floods, but now we have also droughts, and droughts are what are actually compromising in a shorter term our flood defenses. So that means that the events or the problems are happening more frequent because droughts is happening more frequent than the flood events. As I said, I'm a very big fan of the inspectors. I think that they do an awesome job, also because they are very well trained to do it during high flood events, by the way. So that's also something that you need to take into account, that even if you have, for example, flying a drone during a storm, it's a bit more difficult than if you, for example, put a person during a storm. So there's a lot of things that inspectors can do better, which means that we need a lot of sensors, a lot of machine learning, and basically the problem is becoming very big, not only because of the technology on accuracy, but because of the size of our system. So I'm going to present today 3 cases. So the first case is where to put some sensors, and how can I use simple machine learning to predict where do I need to install some sensors so I get the best monitoring strategy. The second one is which dikes are more prone to cracks. So basically, we're going to use this type of information, a combination of information to predict which dikes are more prone to drought cracking. And finally, how to detect cracks with distributed temperature sensors, fiber optic based sensors. So that's something different, for example, for what we have talked today with drones. And these are the people that basically have done these studies. They are the main authors of these studies. I was lucky enough to get these super smart students and supervise them, but most of the ideas I'm presenting here are not mine, they're theirs, okay? So let's start. First is the one Manuel. Manuel is a former student from TU Dresden. He came here to do the master thesis, and now he's actually doing his PhD, and I am supervising him now because one of my favorite topics is piping erosion modeling. And basically, when he came here, the question was like, I was working in some models for prediction of piping erosion, but the question that he was solved in his thesis was like, where to put a sensor underneath a dike so that we are able to better predict if piping is happening or not, okay? And for that, we have 2 scenarios. The scenarios in which I can put the sensor wherever I want, so all these gray dots are sensors wherever I want, and the scenario that I am more keen to offer the waterboard, which is I'm not going to drill a hole underneath your dike. So I'm going to try to install the sensors outside the dike. My performance most probably will be less, but then at least I'm not going to generate seepage paths, because it's going to be a bit stupid if I say I'm going to predict piping by generating piping, right? Okay, so the first thing, and just to brag a bit more, this is the model that we created with Manuel. This is one of the first time-dependent models that are, let's say, available for use, because there's a couple of them that were produced before us, but the reproducibility of those models is very difficult. Whereas our model, we have a cooking recipe of how to build it in a finite element model commercial software, and we were able to predict how piping progresses in time. The model is good or bad, that's a different discussion for a different talk. But we have a model so we can predict in time how piping progresses, okay? So now the question is where to put these, where to put these sensors. But before that, basically, we are going to use machine learning, very simple machine learning techniques to define that. And I'm going to explain very fast what is the machine learning technique. So if you see the plot in this side, basically, imagine that I collected 2 variables, whatever variables are, okay? And when I plot one against the other one, then you can see that I have a lot of spreading in one direction and a lot of spreading in the other direction, right? Assuming that they are normally distributed, so there's a lot of uncertainty. So principal component analysis, what allows me is to find which is the projection of axis along this data, because the normal one will be this one, x and y, the normal that we will use. But I'm going to try to find what is the best projection axis, so that I reduce that variance, or at least I translate it to only one dimension. And what I see here is that basically if I take the same axis and plot the same data, you will see that there's still a lot of variance in this direction and a bit of variance in this one. So what I can do is I say, okay, I forget about this 6% variance that is affecting my model, okay? So I'm gonna make my model a bit less accurate, but I'm going to be able to predict the same process only with one variable, right? Because it's a projection in this direction. So if I know this variable and this variable, I just need to project this one here, and I'm already accounting by this inclination of the path for the variance from the other side of the variable. This is very easy to plot it like this, because it's 2 dimensions, but when the problem becomes 100 dimensions, which is basically machine learning, the problem becomes a bit more complicated. Now, this is another interesting thing. Principal component analysis nowadays is a machine learning method. When I was in the university 25 years ago, it was just a statistical method, but now it's a machine learning method, and the reason is because we can do it very fast. And there's also other derivations of principal component analysis. You can have Fourier principal component analysis, nonlinear principal component analysis, but the basic concept is the same. It's a dimension reduction method. So now the results. Whoever has worked in principal component analysis, and if you haven't, I'm going to give you already a hint, you always end up with 2 or 3 components. And the reason is because this is so linear that basically every time he's always going to have like something that is favoring the projection in one direction, so that doesn't matter. The whole point is that I'm going to be able to account for most of the variance of the model, most of the craziness of the model with 2 components. In this case, basically we ended up with 2 components. One component explained 90-something% of the variance. The other component explained a bit less than 10. Sorry, another explained like 7 or 8, if I'm correct, and the other one explained like 1%. Which basically means that when we plotted, we transform these variables and we plot them how they see in time. Basically, these are the 2, how they look in time, right? So we took our model, we run it, the piping model, and in time, basically, we took all of these sensors, and we calculated the principal components, and we saw that there's 2 main signals. So if we can recreate these 2 main signals, then basically we are able to predict piping. So then, the interesting thing is that we used a model of an experiment of piping failure that was done here in the past in the Netherlands called the dike. And we know from the dike, for example, we know more or less what is, and from the model, we know what is the rate of progression of the pipe. It's this red one. So how the pipe length develop in time in the experiment. And we also know the water loading, because during the experiment, basically we increased the load, or they increased the load. I was not even here in the Netherlands, by the way. So they increased the load. And basically what we see is that one principal component looks a lot like the loading, and another principal component looks a lot like the progression. So now the next question is, from all these possible locations of sensors, where can I place the best placement of sensors? So the only thing I needed is to take the signal of pressure from the model in each of these locations and analyze the correlation with this component. And then basically, if I'm able to install the best correlated sensors to the components with 1, 2, or in this case 2 sensors, I'm going to be able to predict piping. All these colorful dots are basically correlation values. So you can see, for example, the farther I am from the dike, the correlation decreases or increases. That depends. But now the question is, first of all, from all these possible combinations, where is the one that I can predict better, piping in terms of the trend, so I can follow the signal, or the other one in terms of the magnitude? That goes also along with what I mentioned before, that in monitoring, basically one thing is detection and another thing is measurement. So you can be correct in your measurement, but not necessarily in the detection, because detection can happen wrong in time. So we posed this as a multi-objective problem in which we wanted to minimize the round mean square error and maximize the correlation. So there's trade-offs, because if I want to be correct in magnitude, I'm not correct in trend, and so back and forth. And we found basically 3 main scenarios from this Pareto diagram. So if I install, for example, the green one, I will maximize the R square, and I'll get, let's say, more or less the second minimal round mean square error. If I use the orange one, the same thing, and if I use the red one, then also now it's a trade-off. So what you can see here is, like, if I am close to the pipe progression, I have, of course, I'm able to predict this line that shows me how the pipe is progressing. And if I am around here, I'm better at predicting the water loading. So this is also very interesting because I could put a standpipe and say, okay, this is how the water loading changes. But there's a transformation of the signal through the soil because the water needs to go through the soil and loses some energy. So actually, some standpipes here underneath the dike will be a much better indicator for piping. Now, the problem is that I cannot go to the water board to say I want to put some pipes underneath. So we did the same problem, but only with this line of sensors. These were the only possibilities. And this is what we get as a solution. The interesting part from here is also that not necessarily the most superficial sensor will perform better. So it has to be something in between. It cannot be very far from the dike because it's too far from the main signal. It cannot be too close to the dike because basically it will be the water loading, which we already have standpipes and we already know the river, for example, what is the water. So it's better something like this. And to prove the point, we simplified this model and we compare it with what we call observation. So observation is basically the finite element model that we developed with Manuel, and the prediction is the reduction with the principal component analysis. In other words, the yellow line I can predict if I have two sensors in place. This flat line that you see here is basically the progression of piping erosion, and this is the pressure after piping erosion. Okay, that's one example. Now I'm going to go to the second example. This is a completely different problem. In this one, we work with Shaniel. Shaniel now is a consultant from Royal Haskoning. By the way, a lot of these companies are also involved in DigiShape, so this is really cool and really interesting because you can see like the loop closing. And basically what we wanted to do here is we wanted to help the water board of Delftland to plan better their inspection routes. Because as we know, there's nothing better than the humans. I will say it again. But we don't have enough humans to inspect the system, so we need to do an optimization problem in which we need to tell the water board, okay, send the inspector first here and first here because this dike is more prone to cracking. This is how the Delftland jurisdiction, let's say, will look like in terms of the regional flood defenses. And this is more or less the scale of a crack that you can have. So cracks can be big, can be small, but the ones, for example, we saw were like this big. And now the question is this big or small for a satellite image? Small? So what do you mean by small?
For satellite images?
Yes.
Satellite image has a resolution of like 1-2 meters. So.
Exactly. So depending on the resolution of the sensor, that's very good, you're going to have some detection. And then the question is this crack dangerous or not for us? And we will talk about for hours if you want to talk about how dangerous are cracks. But for this talk, basically, what I'm going to point out is that the size of the crack that you can predict depends also on the resolution and the spatial frequency and the time frequency that you can predict them. So we were also very lucky because a lot of these cracks happen very close by here in the ski caddy. So in the skiway behind, a lot of these cracks happens in this canal. So we were able to do the model and go and check walking if the crack was there or not. Another important thing that now I cannot show because Microsoft doesn't allow me to. The cracks that I see today, not necessarily are the cracks that I'm going to see tomorrow. And the cracks that I see tomorrow, maybe I will see them the day after tomorrow. So the cracks are a very dynamic environment. Like here in the department, TU Delft, and I myself, I've been more or less 10 years studying different behavior of cracks. And what I can tell is that cracks are a very, very complicated process because it also depends not only on the drought, but it also depends on the materials that are there and the tensile stresses that you can exert. So for example, if the dike has a certain type of grass, you will have a different type of crack, and you will have a different time span for the crack to occur. So we were very lucky because the water board of Delftland collected a lot of cracks. This is a very interesting database, if you ask me, because it was very well collected. So we had inspections of 2018, 2019, and 2020, in which they basically define all these characteristics of the cracks. And just to point out a bit of reference, so if we do an histogram of the depth of the cracks and the length, we have that most of the cracks are like 1 meter length, the ones that were inspected, but you can find, let's say, 0.5 kilometer crack. They were able to observe 0.5 kilometer cracks in these inspections. But in terms of the depth, it's a bit more uniform. And the reason is because I cannot go deeper. For example, if I have a clay layer, there's a moment where the clay will not be able to fracture more because of tensile stresses and other reasons. I don't want to go in technicalities, but this is very well defined by the physics. So predicting this value is a bit easier with a physical model, for example. So how we can predict them? First of all, we need to do data augmentation, because the problem with the data that we have from the inspections is that it's data from ourselves, so from the cracks, but not from the drivers that create the cracks. So for data augmentation here, what we did is, in a GIS environment, we located the cracks in history, and we started overlapping this data with a lot of other different data that we as crack experts know that are influencing the process. For example, the rainfall, the evaporation, the subsidence, the NDVI, or the greenness, let's say, of the grass, the precipitation deficit, because there's a lot of things that are related to drought based on what we call here in the Netherlands SPI or SPIX drought index, which basically means the cumulative number of days that I'm having droughts. So that's basically the indicator. You have to bear in mind that when you're predicting droughts, basically you're predicting zeros. So it's very difficult if I predict 0 today, 0 tomorrow, 0 tomorrow. It's better to use with cumulative or with the history of the precipitation and the evaporation. And another very cool one is the levee orientation, because depending on how the levee is oriented with respect to north to south, basically it will be more exposed to the wind and to the sun. So there are some dikes that just by their orientation will be more prone to cracking. And this slide is just to point out that all these different sensors have different resolutions and different time frequencies. So building models by combining this data, it's a bit difficult because basically you're restricted by the coarser resolution. You can downscale the information, but that's also a big danger because basically you're including more uncertainty in your problem. So you should work basically with what you can base on the frequency and the amount of overexpression in time and the spatial resolution. So some examples here, for example, of the different data that was used. So most of this data is remote sensing data and the physical observations also. Some of these are also produced maps, so not necessarily measured data from the field, but knowledge, for example, that Deltares has developed in terms of the type of soil, for example, or what it's called the soil flexibility, which is a bit of a weird concept because basically the soil flexibility is how much the soil will deform if it's loaded on top. And the question is if it's loaded or not. And then with all this data, we did an association analysis. An association analysis is something similar to a correlation analysis, but the problem is that these are discrete variables and non-hierarchical variables, which means that we are analyzing here, for example, the size of the crack, which is a continuous variable. You know, it can measure different distances with respect to if it's white or black, or if it occurs a crack or not. So you see, these are binary data which are not necessarily measurable, and therefore what we do is an association analysis. And from the association analysis, what we found out is that, first of all, NDVI, subsidence, and precipitation deficits are the best descriptors of the problem, but conditioned to the size of the crack. So sometimes if the crack is small, and by small we define the length less than 2 meters, especially because some of the, as you said, some of the satellite imagery has a resolution of 1 meter. So we said, okay, we need to determine that a crack is influenced by a certain environmental driver if it fits in 2 pixels of 1 meter. And what we saw here is that if we added the whole data set for all the cracks, basically for smaller cracks, the influence is less than when you talk about only big cracks. So then, this is where we use the machine learning component. So we use something called a model decision tree. So basically, it's an algorithm that, in principle, works as a classifier. So it splits the data in groups. And these groups, basically, these splitting thresholds tell me things as an expert. For example, we learned here that if the flexibility was less than 0.573, in other words, if the soil is not very flexible, cracks cannot occur. In this one, for example, we learned that cracks will only occur if subsidence and drought will happen at the same time, and that is for model 2. So that means that if I'm going to be really sure for a small crack, I need subsidence and drought to occur, whereas that's not the case for the big cracks. Okay? And finally, so how this looks in an operational way. So we took this model and we took all the dikes from the water board of Delftland and we compare with their know-how. So their know-how basically is they already have a lot of knowledge and expertise of walking these dikes for years. So they already have maps in which they rank the dikes for more prone to cracking or less prone to cracking. And we compare it with our model. Of course, this is a testing data set, so we didn't have these points included in the training of the original model. And what we could find out is that, first of all, the knowledge of the waterboard is very good. Like these two maps align very well to each other, but we managed to reduce the points of inspection by a lot. So they don't have to walk the whole dike, but we already told them, like, look, in these locations, you can inspect first at least. And there's other conclusions that are included there, but I think we will distribute the presentation, so for the sake of time. And the last application basically is how to detect cracks based on fiber optic sensors. So these, by the way, I missed also this. All these things that I'm presenting today are already published. So all the references are there, either as in the form of the master thesis of the students or their own publication. The only thing that is not published is this one, the last part, which I am working right now. So this is ongoing work. This is not final. And this was part, of course, also of a small project of a grant for the Idea Generator initiative from NWO. So basically with that sponsoring, we managed to do the experiments, buy equipment, and hire Leonardo, who is the postdoc I was talking before. So first of all, I'm going to explain how fiber optics work. It's a relatively simple concept. So it's the normal telecommunication cable that you use at home to bring internet. So these cables do not have electricity. They work with photonics, with light. So it's beams of light which are thrown at a certain frequency through the cable. And that's how basically we transmit the information. Now, the interesting thing is that fiberglass itself, or glass fiber, let's say, it's very sensitive to temperature and strain. So if I touch it or if I bend it, it's very sensitive. And what it means is that its atomic structure reorganizes very fast. And this atomic structure also has impurities. So it's not only glass, there's also other things, or derived products from silica that are in there. But if these things reorganize, what it means is that the properties of light to flow through the cable also change, which means that if I, for example, I hit the cable, the atoms reorganize, and then the amount of light that will propagate through the glass will change, which in other words allows us to use the cable as a distributed sensor because it can measure temperature base as long as it's touching something that is changing in temperature, okay? And yeah, the physics of it, basically, you throw a lot of different beams through the cable, and some of the light goes pass through, and some of the light comes back. So basically, I generate like a kind of what we call here a backscatter spectrum histogram. And depending on the property that is affecting the cable, if it's heat or if it's strain, one of these anti-Stokes or Stokes parts of the spectrum will change, and that I can relate linearly to a change in temperature. So the experiment consisted, it was done here at Floodproof Holland. Floodproof Holland is the lab that we have here for dikes just behind Deltares. And it consisted in monitoring a dike for 3 months. And it's a dike that we already knew that it was very prone to cracking. How do you know that a dike is very prone to cracking? If it has a lot of peat. Peat is a very difficult material, a very crazy material that we have it abundantly in our dikes here in the Netherlands, I will say. And basically, peat has the property of storing a lot of water. So when peat is saturated, it's something around 1.6 tons. And when it's completely dry, it can go like a cubic meter, it can go to 600 kilos. So it changes its weight very easily, and therefore it's easier to crack. So we took this dike and we installed basically 3 different sensors. We installed a thermal camera, which has a resolution of 3020 by 256 pixels. So this is how the pictures look like. We installed the fiber optic cable, and basically we installed 32 lines. It's one single cable, but in 32 lines along the dike, spaced every 0.5 meters, as you can see it here. And we also installed a webcam. And the reason for the webcam is because the webcam can capture the greenness. So we were also going to use the NDVI. And after monitoring 3 months, this is how the DTS looks like. So basically, I take all these cables. Every 20 centimeters is like I have a sensor, and then I do an interpolation, and this is how the temperature looks like. By the way, we monitor a crack. We already knew that there was a crack there, which I am very happy because basically we wanted to do the experiment for drought, and it ended up being an experiment for floods because it was during June of 2021, which we had the floods in Limburg. So gladly the crack was there because there were no new cracks generated, but we could still monitor the thermal response of the crack, and that's what the paper from Simone is about. But if you see here, in this little square, basically we have, if I cut a chunk of this in this interpolation, it looks like this. This will be like the interpolation that comes from the DTS, and this is how the thermal camera looks like, and we were taking pictures every half an hour, which means that we could use the signal of the sensor, and with some deep learning technology, which is called image-to-image, which basically you feed images to produce more images or image generation, we were able to use the sensor data to produce the pictures that we were already taking from the thermal camera. So ideally, I don't need a camera to see in the field, but if I know the signal from the DTS, I will be able to predict a picture that looks a bit like that. However, all these algorithms, especially the ones of deep learning, they are developed for big data, which means that you need to make sure that you have enough data, and by enough data, it's not just the number of unknowns or weights that you are calibrating, but it should be way more because this is an optimization problem. So you need to satisfy as many possible situations in your training. So what we did is we take the pictures and we split it in 4. So originally we had 992 images, and then when we split it in 4, we ended up in 3,968, but the resolution now it's 128 times 160. And then we also added 3 different cropping patterns because we wanted to include, for example, images in which you have crack and cable, images where you have crack but not cable, and images where you have cable but not crack. So that basically ended up as having 2,976 more images. And then with image processing, data augmentation can be also done by flipping the images. So you turn them around or you mirror them. So with this process, basically we ended up in a data augmentation data set of 31,745 images of 160 times 128. We trained the model by 600 epoch, and this is how it looks like. So this is the input after the interpolation, the simple interpolation from the DTS. This is how it should look like, and this is how it looks right now. Not very promising yet, but you can already see that there are some patterns that he is capturing. So for example, when you have high heat in the middle close to the cable, he's predicting high heat close to the cable. In this one, for example, this is a different, because of the resolution, this is a different location than this one, and you can already see the heat patterns here. In this one, you can already see 2 here and 2 here, 2 here, 2 here. In this one, you should be able to see the crack. In this one, I think you more or less see the crack, and in this one, you should not be able to see anything, and it's also confusing. So the error at the end from this model, right now it's based on the data from training, which needs to be reduced, let's say, or normalized. But the estimation that we have is that we're having in average an error of 1.4 degrees Celsius. To be honest, it's not really necessary to have the measurement correctly. What we need to have correctly is the gradients, because the way to detect the crack is just a difference in color, let's say. So if the crack inside is 100 Celsius, which is not possible, but the pattern is correctly identified, we will be able to detect the cracks. So as a conclusion, or the main conclusions, machine learning can be used to design sensor systems based on dimensionality reduction. That's what we showed in the first case. AI requires sensors before being operational and after becoming operational. So depending on the use of the sensor, basically you're going to have a different, let's say, a different impact in your machine learning system. And that is also because of the difference in resolution. Sensor combination can pose a challenge in machine learning and in AI due to its variability and frequency of spatial resolution. So having a lot of data doesn't mean that you really have a lot of data, because one data set basically can constrain the other data sets. And AI and ML are tools for knowledge augmentation. That's really, really important. The AI is not the tool or the model. It's just a tool for being able to understand better the processes. So I also think that we should not dislink it from the physics. However, their capacity is completely determined by the sensor with highest spatial resolution and frequency. This is what I said before. Thank you very much.